nanohub.org.
Online simulation, and more for nanotechnology.
Hello, everyone. Thank you for coming to my talk. Today, I'll be talking about how our group has utilized NanoHub and the utilities available there to develop an application called Pigment Hunter. And yeah, basically, it's an app that explores how the protein dynamics and spectroscopy, how to predict the optical spectra of these proteins. Let me start with acknowledgements. These are my advisor and my lab-mate. They both worked on the project. I would like to thank NanoHub for hosting the application and ITAP for all their technical help. And Dr. Rochatano for his GROMACS force fields that he gave us, and Dr. Ranger for his transition partial charges, and of course the Department of Energy for funding this project. Okay, just an overview of the talk. I'll go into the background and significance, like why this app was needed. Then I'll talk about the app itself and then show how the application can be applied to different systems. So background and significance. So right now, the main motivation for this is what we want to learn what is the connection between a protein structure and the optical spectrum we get in experiment. The issue is this in between, it's like a black box. We're trying to develop a tool that can predict that spectrum. But the problem is when we are running these calculations by hand, these take a lot of time and they have a lot of steps and they can be very complicated and tedious. So you're more likely to make mistakes. In our vision we had was an ideal way to do this would be to have a user-friendly graphical interface so that someone who doesn't know how to use GROMACS or any of these other softwares that we used could go in and use it without much complications. We wanted something that wouldn't require a software installation, so something that could run remotely, like somewhere else, not necessarily on your laptop or your computer. We wanted something that could run molecular dynamics on these systems. We wanted something that could also predict optical spectrum. And most importantly, we wanted something that was computationally inexpensive. So our solution was an application that we developed called Pigment Hunter, which is a point-and-click simulation tool. It is available on NanoHub's website currently. And basically, this tool has taken the process of taking a protein data bank structure or a crystal structure of a protein from the beginning to the end of predicting an optical spectrum. So let's go into the application itself. So just an overview of how the workflow in Pigment Hunter works. We start with a PDB protein structure. And typically these structures, they're not complete. They have some missing atoms or they have some like slight errors or something. You upload it or you can grab it directly from the website. You send it in and you can repair and mutate that structure and run molecular dynamics on that structure, and then finally predict an optical spectrum. And the way it works is it will identify the pigments in the structure, and you'll be able to visualize them in the main window. It will repair any errors, like any missing atoms in the pigment or protein, and it'll use biosymmetry operations to help with that. It will prepare and run the MD simulations with trajectories, and finally, it will apply the Frankel-Exciton model to be able to calculate the optical spectrum from these structures. I'm going to go into a little detail on each of these steps. The first one is characterizing the pigments. So when you open up the application, this will be the first screen you see. This is the main window. I have pasted a QR code here if you're curious. But yeah, so like when you open it, the first thing you'll do is you'll go to the load tab and you can load any structure you want. For this protein, this is water-soluble chlorophyll protein. The ID that I used was the 2DRE one. You could either fetch it directly from the website, or you can also upload a protein structure file if you have one downloaded. And typically when you pass it through, you can go either to any of these steps directly. The first one is repair. So if you go into the repair, this is where you can fix any of the issues that might be with the structure itself. This second option here is to build the exciton models. And this is where you can calculate the optical spectrum and then analyze the spectra as well. And then the final option is build MD model. And this is the process of running it through GROMACS and doing the molecular dynamics on it. So you'll have like multiple windows that pop up. The first one will be your MD launch, which you can load whatever structure you wish to focus on. Then the MD organizer, which will have highlighted these options for you, where you would build the topology, mutate the structure, minimize and add hydrogens to the pigments, and then energy minimize the system. And we'll go into more detail for all these in a little bit. So some of the things that made NanoHub really nice for developing such a tool was that it had a lot of embedded libraries that other sources did not. The main ones that we used for like making just the interface itself, like the way how everything looks, like the buttons and stuff, are IPyWidgets and HubLib. And then to visualize the molecules, we ended up using NGLView. The other nice embedded libraries that NanoHub had were ParMed and GROMACS. And these were used to parse through the PDB structures and like edit and like run them like thermodynamics. And that plays into a big role in this build MD model step. So just to go into a little bit about these IPyWidgets and NGLView, the nice thing is IPyWidgets are quite relatively easy to use. Like if you would load the module, and then you can write like anything. For example, in this is a float text, sort of like widget, I would say. And you can adjust it. So like if you wanted it to like show a specific value or have a description or something, you can enable or disable it as well. It's quite easy to just like code into it. So NGLView, this is used more for the visualization of the structure and the trajectory. This is a little more tricky, but like again, it is for the most part friendly, user-friendly enough that, and it is incorporated into NanoHubs. So it's really nice. So I said we were going to characterize pigments. This is the first step for Pigment Hunter. So there are 4 pigments that our application focuses primarily on for now. They're chlorophyll A, geophytin A, chlorophyll B, and bacterial chlorophyll A. And in the PDB structure, when you have these databank files, they have these 3-letter codes, and these will identify what the structure, like which structure is which. This chart just goes through, these are different models that we've incorporated into our app. And it just shows like, okay, like for example, for chlorophyll A, you can run all these simulations for it. But for chlorophyll B, you can't do the molecular dynamics and CDC. For almost all of them, you should be able to run the first 3. CDC is dependent on if you have molecular dynamics completed or not. The next next step that I showed you is the repairs part of the application. So pigment repairs and biosymmetry operations. This is a chlorophyll molecule for the just to show an example. So basically what the repair tool does is it looks and analyzes, okay, like this is supposed to be a chlorophyll A, but it's missing X or Y atom. So it'll try to insert the atom and try to make it fit in the correct manner. The other nice thing is when you upload the structure into the repair tool itself, sometimes the crystal structures, they come in forms of a monomer or a dimer. Like in this case, this is FMO complex, I think 3ENI. This is the PDB code. And it's shown as 2 monomers. But in reality, it's supposed to be a trimer. And what the repair tool does is it looks at the molecule and performs biosymmetry operation to create the final monomer and complete the structure. Okay. So this page, once you have repaired the structure, you can go back and load the structure into the main window and continue on with the molecular dynamics. The first step in the molecular dynamics is building the protein topology and mutating the structure if you choose to mutate it. And this is what that page would look like. You would open it up. So you would visualize the protein here. You have the option to mutate a residue. So for example, in this example that I've shown, this is still the water-soluble chlorophyll protein. But what I've done is I've selected the glutamine 57 site and I've mutated it to alanine. And you can go through and select however many sites you want or whatever sites you want to focus on. You would hit mutate and it will add it to the list. And then you would hit build topology and it will run through and build the topology. Now, the way it works is it works in a very iterative process. So like, as you can see, there's multiple rounds. It'll go through and check for, if there's any chain breaks or missing atoms or anything like that. It'll try to correct for those. So it'll go through once, if it finds that error, it will go through it again once it fixes that to see if it's fixed the error or not. And it'll continue that until you finally have the final round, which will be a success. And the nice thing here is we have a feature where you can click on any of these like changes that have happened. Like if I clicked here, it will show me the bond that it fixed. Or like if I clicked on the glutamine 57C, it will show me where that site is. And another thing that's nice is we've incorporated is the ability to see exactly what's going on in the GROMACS run, like what error messages and what's exactly happening in that while you're sitting there watching the simulation happen. Yeah, so this is more a zoomed in view of the window. Again, this is just like showing the different options you have. Like for mutation, you can either remove mutations, and you can go into each of these and see the details of each of the runs, each of the iterations. And panel A shows the mutation from glutamine to alanine. And panel B shows like the fix in the chain. Okay, so now that you've loaded the structure and did the initial topology and fixed any like minor errors that could be in there, the next step in the molecular dynamics organizer, after you build the protein topology, is to build the pigment topology. And the nice thing about this organizer is that you can keep track of which steps you've done. And for example, if I had not completed the pigment topology, if I come back the next day to try to do something, I had not completed it, and I cannot continue to the next step. So you would have to validate, did it work or not, or did I finish it or not? And then you can move on. So the other nice thing about NanoHub is that we have the option to submit these jobs to our standby queue for the Negishi cluster here at Purdue. So all these jobs that you're running, they will not be run on your local machine at all. They will all be sent to a remote computer. So for the molecular dynamics itself, we've implemented Timel and GROMACS. And here I've shown like just a basic overview of the app, a very fundamental overview. In red, I've highlighted where GROMACS is used. So GROMACS is used for the entirety of this step, and it's used in each of these 4 sub-steps. Timel script is used in the protein topology mutation to help with mutating the structure. Other minor things. Okay, now you've had a completely energy minimized structure. You've gone from like a PDB file to that a complete structure. So the next step is predicting the optical spectrum. So just to like remind, like what we have is like the structure. We have an experimental idea of what the spectrum should look like, but we don't know how to get to that. So one of the models that people use is the Frankel-Exciton model. The Frankel-Exciton model this is just a brief overview of each of the different minor models that we have incorporated in the application. Frankel-Exciton, the way it calculates the shifts or energies is by doing a combination of the electronic coupling, so the interaction between 2 sites or 2 pigments in this case. And these, if you look at the matrix, these are supposed to be your off-diagonal elements. And then the other component is your site energies, which is your on-diagonal elements. And these are your interaction of the site with the surrounding environment, the protein, the solvent, everything. We've incorporated for each of these 2 different models. For the electronic coupling model, the first one is the PDC point dipole coupling. And basically it's looking at where the dipole moment is and finding the center and calculating that one value, the one coupling value for that. This is a very simple model. It's very basic, can be applied to a lot more systems. The more refined model that we use, this is where Dr. Ranger's work comes in, is TRESP. And this is based on his transition partial charges. And basically what it does is it goes through and looks at how one atom interacts with each and every atom on the other structure. Then it goes to the next atom and the next atom. You'll end up with a summation of different interactions. Now on the site energy side, we have two models. We have charge density coupling, and this is looking at how the charge is affected by the environment, the electrostatics of the chlorophyll with the environment. And finally, we have NSD for the site energies, and this is looking at how the ring bends and how it deforms and how that affects the site energy as well. So when you load the structure after you've done everything, on the main page, you go to build exciton model. You'll see features like this. You'll note that even though we have the TRESP PDC, we have a uniform site energy model and NSD, we don't have the CDC option here. The only time CDC option will appear here is if you've run the molecular dynamics. If you haven't run the molecular dynamics on a structure, you won't be able to use that. But you can always upload an external charge file if you do have one. Once you have loaded and you've selected which models you want to use, you click Simulate, and it'll take you to your spectrum calculation page. And here we've, again, you can load any of the models that you've created. You can change the temperature, you can mess with the disorder and the coupling, and if you want to incorporate vibrations or photons into the spectrum or not. You have a lot of freedom to adjust things. So yeah, this is just to show. So in figure A, we have calculated the spectrum for WSCP, like water-soluble chlorophyll protein wild type, without the coupling incorporated. And then in figure B, we've run it with a coupling. And like you can see, we have the fluorescence spectrum and the absorbance spectrum. But in the figure A, you don't get the circular dichroism spectrum. But with the coupling, you can get that. Okay. So just a brief overview of how the app works is you'll load your protein structure. You'll have the option to go into molecular dynamics or exciton modeling or go to the repair tool. From the repair tool, you can go back and do either the molecular dynamics or build an exciton or go straight to the optical spectrum calculation. Within molecular dynamics, you have 4 steps. You have the protein topology creation, and then any mutations or things like that you want to incorporate. You have the pigment topology and the adding of hydrogens and minimizing those hydrogens. And then you have this total energy minimization steps. Once you're done with molecular dynamics, you can push it through to the exciton model. And after you've built your exciton model, you can go and calculate your optical spectrum. On the right hand, we have how our files are organized. So anytime you see the feature that says download, you can click on download and it'll take you to the data folder. And within the data folder, you can have a couple different options. If you want any of the data from the exciton models, you can go into the EXC folder and it'll show like a list of like 6 files that are listed here. For molecular dynamics, you would hit MD, and within that there are 3 subfolders, 4 subfolders for each of the steps. And then molecular dynamic organizer is just the notebook for that. Okay. So I'll just go through some different examples of how we've used the app in some of our work. Okay. So the first publication our group published back in 2021 was this paper by Dr. Srivastava. He was a postdoc in our lab. He did a project on point mutations for water-soluble chlorophyll protein, and we were looking at electrostatic shifts for the protein. So basically what his whole focus was on this glutamine 57 site, and he would do point mutations there. And once he would mutate them, he collected experimental data and found the shift between the wild type and the mutated spectrum. So what we did was we recreated this in the simulations from Pigment Hunter to see how the Pigment Hunter app correlated with the experiment. And you can see here, we have a strong positive correlation for the most part. We did have an outlier here, but we're working on figuring out what is going on with this guy. A more recent publication that just came out, like I think a month ago, is Chen Su's work, which is on the ring deformation calculations for site energies. So yeah, the ring distortion, basically, in this example, we're using photosystem 1 and photosystem 2. So photosystem 1 in red and photosystem 2 in blue. And these are different ring deformations in the last row here in D, E, and F. And you can see how the chlorophyll like ring looks different for each of them, how it's bent. And then the results are different as well because of that. This is focusing on the site energy. Both of these were focusing on the site energies of the protein. Yeah. Another example that we had dealing with site energies is comparing our Pigment Hunter site energy model to a more accurate and computationally expensive model. So Dr. Kim, he did work on quantum mechanical, molecular mechanical simulations on bacteria chlorophyll protein, FMO. And as you can see, we will go through each of the frames and look at to see how our CDC model compares to it. And that's what's shown in frame A. Yeah, so the B frame. B is your how we're comparing the results from Pigment Hunter absorbance and circular dichroism with experimental results at 295 Kelvin. And C is the same, except it's at 77 Kelvin. Panel D, I'm showing the structure. When we ran these calculations in Pigment Hunter, the FMO has 8 chlorophylls in the monomer, but the 8th chlorophyll is missing a tail. And as of right now, we don't have that feature to add the tail. So we decided to remove that chlorophyll and run the calculation with just the 7 pigments. So the last thing we wanted to show was how the exotomic parameters affect the spectrum shifts as well. So for each of these simulations, this is light harvesting complex 2. And we ran each of these simulations at 5 Kelvin and used transition charge couplings, so TRESP, transition electrostatic potentials. And we set the Gaussian dose order full width half max to 500 wave numbers for B850 ring and 145 wave numbers for the B800 ring. So the first frame on in B is the uniform site energies. In this case, for site energies, we set all the pigments, all the rings to a site energy of 12,500 wave numbers. When we go to the next frame, this is the shifted spectrum. So what we did was we took the values from literature, and for B850, we set it to 12,110 wave numbers, and then for the B800, we sent it to 12,510 wave numbers. And you can see that just by adding shifted site energies, already the spectrum is starting to change. In panel D, what we've done is we've incorporated the phonons option in our spectrum calculation page, and we set S to be 0.8. And you can see that in the first 3 frames how it shifts and changes the spectrum in the calculations. And finally, in frame E, we have the experimental data, so you can compare how each of the steps were compared to that. Okay, yeah, so just want to give a brief conclusion. So with the Pigment Hunter application, we have demonstrated, and through this presentation, we have demonstrated how NanoHub has all these great capabilities of creating these softwares. It allows us to make a user-friendly graphical interface. It allowed us to automate the molecular dynamics process and using GROMACS. And it allowed us to automate the process of calculating this optical spectrum from these exciton models. All of these steps individually would have taken a long time, just getting to know how to use these programs by hand and running the dynamics and then using the calculations to calculate the spectrum. The last point I wanted to give was that we have a publication that is in press as of right now. And yeah, that is it from me.
Thank you so much, Zampa. Seth asks, is it only limited to molecular dynamics?
As of right now, we have GROMACS installed onto the app, and we can run molecular dynamics, but you don't have to run the molecular dynamics.
Also, question is, can you give an example of how someone could use this tool and do a new research project?
Yes. I would say one benefit of this tool is that you can, like, let's say you're working in the lab and you don't really want to spend a lot of time creating mutants or doing something like that. One thing Pigment Hunter can do is you can use Pigment Hunter to get a prediction of what results you would expect before you go into the lab.
I'll jump in here real quick on the application mode question. This is one of the more complicated things about writing an app, but is figuring out how to write the correct invoke script. But there is an easy solution, which is to find an app that does something similar and look at the source code. And in most cases, that'll get you what you need. Just find an app on NanoHub already that does what you want or something similar, and simply copy the invoke file and modify the file names.
Thanks so much for that, Mike. And then we do have another question. Can one run MD on NAPDB structure, or do we need other inputs?
Yeah, so for this application, it's more for photosynthetic pigment complexes, protein pigment complexes, than it is for just general pigments.
Yeah, that's actually a great point. In principle, you could run it on anything. The app right now is set up to run, as Safa says, only photosynthetic proteins or chlorophyll binding proteins. I believe there is another app on NanoHub. Safa, do you remember the name of that app that's geared toward more general MD?
I do not. I can look it up.
NanoGROMACS or something like that?
There is something like that.
Something like NanoGROMACS. There is the features are different, but does a similar thing, but geared toward more general proteins. So check out. I believe it's called NanoGROMACS.
Yeah, it's NanoGROMACS.
Okay, thanks.
Oh, it looks like we have one more question. What are the limitations of this tool?
Safa, maybe we can take this one together.
Yeah.
I mean, there's lots of limitations, right? Do you have any you want to start with, Safa?
Well, I think one of the biggest ones is, like, right now, our molecular dynamics, everything is done in gas phase. We've only incorporated that as of right now.
That's right.
Yeah, that's probably the biggest one in my eyes.
Yeah, that's right. For the applications we've done so far, gas phase MD has been enough, and very short MD trajectories. We really are just trying to, like, initialize the protein and get charges and stuff accurately. That's a sort of a computational limitation or a compute power limitation on the standby queue, but we are working to add more solvent and longer trajectories. I guess maybe another question, I think, the question from Seth earlier about whether it's limited to only molecular dynamics, that may have been geared toward thinking about other tools like electronic structure or other methods. And at the moment, we don't do any electronic structure calculations, DFT calculations, et cetera. But yeah, Safa's chuckling. Sorry, in Pigment Hunter, we don't do. Safa does do electronic structure calculations in general. But yeah, that's something that we're also sort of long term we would like to incorporate into the app directly. I think there are some resources for that on NanoHub, and long term we will try to integrate more electronic structure calculations in.
Also, the site energy calculations, like, they're more accurate for symmetric systems rather than asymmetric systems.
Yeah.
All right, well, I guess if there's no other questions, we will go ahead and close the webinar. Safa, thank you so much for your presentation today. It was wonderful. We learned a lot of great information.
Thank you so much for having us.